Hello, dear students. Today we are continue our lessons by technological foundation of mechanical engineering, and we are start our laboratory works. The name of our laboratory work is Development of the Technological Process, Analytical Calculation of Machining Allowances, and Processing of flat surfaces with the achievement of accuracy and roughness specified by the drawing. The purpose of the work is to master the analytical calculation of machining allowances for sequential processing of flat opposite surfaces with the achievement of accuracy and roughness specified by the drawing. Please write down to your notes the theme of our laboratory work and the purpose of the work and equipment, instruments, and accessories. So, equipment, instruments, and accessories. It's first, universal milling machine, cutting tool, cylindrical milling cutter. The workpiece is installed in a machine vise, and measuring tools, caliper, micrometer from 25 to 50, and metal ruler. Please write down to your notes the purpose of the work, equipment, instruments, and accessories. And work sequence. First, read the guidelines and recommended literature. Second, make a sketch of the workpiece and a drawing of the workpiece, like in figure 1.2. The size of the surface to be treated is indicated by the teacher. Make up the technological process of machining a given surface. Calculate analytically transition allowances, minimum, maximum, and calculated. Find the limit dimensions for transitions and the limit dimensions of the workpiece. Draw a diagram of the location of allowances and tolerances. Insert the actual values obtained during the calculation. Define processing modes for raw and finishing transitions. Calculate the main technological time. and brief theoretical statements. The development of the technological process of mechanical processing, being with the selection of technological installation basis and the plan of mechanical processing at the same time, the issue of the number of row and finishing transitions is resolved. Knowing the sequence of technological transitions, it is possible to calculate the allowance for mechanical processing. In the case of sequential processing of flat opposite surfaces, there is an asymmetric allowance. In this case, the value of the minimum allowance for this transition is determined by the formula 1.1. Z suffix I minimum is equal to the sum of R Z suffix I minus 1, H suffix I minus 1, rho suffix I minus 1, and E suffix I. I minus 1 is the previous transition. In this formula, R suffix Z I minus 1, R Z, is the height of the micro irregularities, its roughness. H suffix I minus 1 is the depth of the defective layer. Rho suffix I minus 1 is the total value of the special deflections of the processed surface of the workpiece at the previous transition. And the last one, E suffix I, is the error of workpiece alignment during installation on the transition being performed. Please write down to your notes this formula and these sentences. For clarity and easy of calculation, the arrangement of allowances and tolerances of the surface is depicted graphically by means of a diagram in figure 3.1. In figure 1, please write down to your notes the scheme of the location of allowances and tolerances. It's the scheme of the location of allowances and tolerances. Write down to your notes. These allowances and tolerance. You have the time to do this. And we are continuing the next slide. Values of tolerances. T of workpiece. Tolerance of the workpiece, and T after rogue. Tolerance obtained after rogue transition. Are determined according to table 3.1 and 3.2 of the appendix. You can see this table 1 and 3. It's on the slide in the appendix of our presentation. Tolerance of the finished part, T of suffix part, according to table 1.2. The minimum allowances, Z suffix I minimum for each transition, are successively calculated according to formula 1. The values of R suffix Z and H suffix I minus 1 are selected according to the table 1.2 and 1.3 of the appendix. When fixing the workpieces in the press-type devices, the clamping force is directed parallel to the underlying support surface and causes the workpieces to rotate. The method can be used for workpieces with the largest width. Therefore, the installation error can be found using the formula 1.2. E suffix I is equal alpha multiplied by B. In this formula, B is the width of the workpiece. Coefficient, it should be taken depending on the nature of the surface that perceives the clamping force. For rock surfaces, alpha is equal 70.5. On subsequent transitions in the same installation, the residual fixing error is so small that it can be neglected. Therefore, when determining the allowance for rogue milling, its value is taken equal to 0. So alpha will be equal 0 for rogue milling. Write down to your notes formula 1.2 and what is the B? Parameter B. General curvature of the workpiece. Rho suffix workpiece is equal delta suffix k multiplied by L divided by 2. Its formula 1.3. Write down to your notes the formula 1.3 and all formulas 1.4, 1.5, 6, and 7, 2. The value of the specific groove delta suffix k is determined according to the table 1 of the appendix. Size big L according to the sketch of the workpiece. When determining the allowance for finishing milling, the amount of residual special deviations rho is taken equal to 0.06 multiplied by rho suffix workpiece. So rho workpiece is equal delta k multiplied by L divided by 2. It's formula 1.3. And rho for rho transition, it's equal 0.06 multiplied by rho workpiece. The values of the maximum and calculated allowances, respectively, for each transition are calculated according to the formulas 1.4, 1.5, 1.6, and 1.7. So that it's allowance of Z suffix I maximum rho. It's equal Z minimum rho plus T of workpiece plus T after rho. ZI maximum finish after finish transition. It's equal ZE minimum finish plus T suffix finished part plus T after all. ZI calculated row is equal ZI minimum row plus T of workpiece. ZI calculated finish is equal ZI minimum finish plus T after finish. Z its allowance, T its tolerance field. Write down to your notes all these formulas. And we start the next slide. Intermediate processing dimensions and limiting dimensions of the workpiece are determined by sequentially adding allowances and tolerances to the limiting dimensions of the finished part with the actual dimensions of the workpiece, after which an appropriate conclusion is made. The depth of cutting for each transition is assigned in accordance with the value of the calculation allowance that I calculated, with rounding up to tenths of a millimeters upwards. The recommended feed values for raw and finishing transitions are selected from table 1.4 of the application and then checked with the passport data of the machine in table 1.5. Smaller feed values closer to the calculated values are accepted. The cutting speed during milling in the conditions of laboratory works is determined according to the standards depending on the already known cutting depth and feed, table 1.6. In general, taking into account the corrected cutting speed V will be equal V tabular multiplied by K1, by K2, by K3, by K4, and by K5. Write down to you know this formula. In this formula, V tabular table value of cutting speed, K1, K2, K3, correction factors depending on the nature of processing, cylindrical milling cutter material being processed. K4, correction factor for crust processing. K5, correction factor depending on the stability period of the cylindrical milling cutter. Please write down to your notes formula and these parameters. Correction coefficient are selected from table 1.7, 1.9. The spindle speed is calculated using the formula 1.8. N it's equal above the line 1000 multiplied by V, it's cutting speed, and under the line P multiplied by D, it's diameter of cutting tool. The resultant speed is compared with the machine data. The nearest lowest speed, N actual, is taken, then the actual cutting speed is calculated, V actual, using formula 1.9. V actual will be equal P multiplied by D multiplied by N actual divided by 1000. And main technological time, T suffix 0, will be equal big L plus small l suffix 1 plus small l suffix 2 divided by S suffix M. In this formula, in formula 1.10, big L is the length of the threaded surface. Threaded surface. L, small l suffix 1, value of cutting tool in feet. And L suffix 2, value of cutting tool exit. S suffix M, it's minute tool feet, it's feet. Please write down to your notes formulas 1.8, 1.9, and 1.10. And of course, the parameters in these formulas. And feed s suffix m row will be equal s suffix z multiplied by z multiplied by n actual. Z is the number of milling cutter teeth. S suffix Z is the feed per 1 milling cutter tooth. And N actual is spindle rotation frequency. And S suffix M finish will be equal as Z multiplied by Z multiplied by N actual. The values of the in-feed small l suffix 1 and exit small l suffix 2 depend on the diameter of the milling cutter, the depth of milling, and are determined by the formula. (1.12). In this formula, T is the milling depth and D its milling cutter diameter. And write down to your notes these formulas and the part sketch with dimensions. You will use these dimensions for calculating by all these formula from 1.1 to 1.12. Write down to your notes the scheme and formulas. And on the next slides, you can see the appendix with table 1.1 deviations allowed for stamped versions of the third complexity group. Table 1.2 accuracy and surface quality of stamped workpieces after machining. Table 1.3 surface quality of forging made by stamping. Table 1.4 recommended feeds per tools when milling planes with cylindrical cutters made of high-speed steel. Table 1.5 passport data of machine. Table 1.6 cutting speeds when milling surfaces with cylindrical high-speed milling cutters with small teeth, processed material, structural steel. And table 1.7 correction factor depending on the nature of processing. Table 1.8 correction factor K2 which depends on the material of the milling cutter. Table 1.9 correction factor K4 during crust processing. And correction factor K5 depending on the stability of the milling cutter with a stability of 60 minutes and working with steel is equal to 1.44. So after that, when you finish this laboratory work, use these check questions, answer on it. These questions, write down to your notes the answers, and when you finish the calculating, please load your works to our course and to our Telegram group. So start your calculation using the parts gauge that you can see on this slide and using all the formulas from 1.1 to 1.12 and using the tables on the appendix, tables from 1.1 to 1.7. Please start your calculation. If you have the question, please write it into our Telegram group or tell me in our lesson. So we have the time. Start the calculation right now. But before you start your calculation, I want to show to you some video about milling. What's the difference between milling and cutting?
Video, we will look into the differences between turning and milling processes. Conventional machining is one type of manufacturing process in which excess material is removed from a preformed blank by shearing in the form of chips using a wedge-shaped cutting tool in order to get desired shape, finish, and tolerance. There exist several machining processes to efficiently machine a wide variety of materials in innumerable ways. Turning and milling are just two examples of such machining processes. So, let's look into the basic differences between turning and milling processes in a tabular form. Difference number 1. Turning is performed to generate a cylindrical or conical surface, whereas milling is performed primarily to generate a flat surface. Number 2. Machine tool that is used for turning operation is called lathe, whereas milling is carried out in milling machine. Number 3. Turning process utilizes a single point cutting tool, called SPTT, which is short form for single point turning tool, whereas milling process utilizes a multi-point cutting tool, called milling cutter. Number 4. In turning, cutting tool continuously remains in contact with workpiece during the operation, whereas, in milling, tooth continuously engages and disengages during operation, intermittent cutting. Number 5. In turning, the workpiece is rotated at fixed revolutions per minute. This rotation provides necessary cutting velocity, whereas, in milling, the cutter is rotated at fixed revolutions per minute. Rotating cutter provides necessary cutting velocity. Number 6. In turning, feed motion is derived by moving the cutting tool carriage, whereas, in milling, feed motion is derived by moving the workpiece, worktable. And difference number 7, turning can produce fragmented, discontinuous, or continuous chips based on work and tool materials, cutting parameters, etc., whereas milling inherently produces discontinuous chips.
In the next video about milling operation. Milling operations.
Plane milling. In this video shows the plane milling operation. Plane milling cutter. Workpiece. Plane milling are used for machining flat and horizontal surfaces.
Plane milling are used for milling of horizontal flat.
This plane milling operation can be otherwise called as slab milling. According to the relative movement between the table and workpiece, the plane milling machine can be classified as up milling and down milling. Up milling. Plane milling cutter. Workpiece. In up milling, the milling cutter rotates in a direction opposite to the feed direction of the workpiece. In up milling, the material is removed by the resultant force. Down milling. Workpiece. Plane milling cutter. In down milling, the direction of milling cutter rotation is the same as the workpiece feed direction. In down milling, the resultant force presses the workpiece against the base. The cutter with high rack angle can be used for down milling. Face milling. Face milling cutter. Workpiece. In face milling, the tool axis is orthogonal to the surface to be generated. In face milling, the tool does not cut with its face, as the name of the method indicates the face milling. The peripheral cutting edges removes metal primarily, and face cutting edges acts as secondary cutting edges. Straddle milling. Workpiece, side milling cutters, arbor, machine vise. Straddle milling is an operation in which a pair of side milling cutters are used for machining two parallel vertical surfaces of a workpiece simultaneously. The distance between the cutter is adjusted by the spacers. Gang milling. Arbor. Side milling cutters. The gang milling is the operation of machining several surfaces of a workpiece simultaneously by feeding the table against a number of milling cutters. This method saves much machining time. In gank milling, the cutter speed is calculated from the cutters of largest diameter. Form milling. The form milling is the operation of producing irregular contours by using form cutters. Convex milling is one of the form milling operation. End milling. End milling cutter. Workpiece. End milling is an operation of producing narrow slots, grooves, ways, and vertical flat surfaces on the workpiece. End milling can be performed vertically, horizontally, or at an angle in reference to the table. Angular milling. Angle milling cutter, workpiece, arbor, table. Let us see the angular milling operation. The angular milling is the operation of producing an angular surface on a workpiece. This angular groove may be single or double angle. T-slot milling. T-slot milling cutter. Workpiece. Let us see the T-slot milling operation. In T-slot milling operation, first, a plain slot is cut on the workpiece by a side milling cutter. Then, the T-slot milling cutter is fed from the one end of the workpiece. Gear milling. For gear milling, we need formed gear cutter, gear blank, and indexing head. Let us see the gear milling operation. The gear milling operation is performed in a horizontal milling machine by using a formed milling cutter. The cutter carries the profile on its cutting edges corresponding to the required profile of the gap between gear teeth.
And now I want to show you the last video about nomenclature of milling cutter.
Nomenclature of milling cutter. Let us see the 3D model of a plain milling cutter. Now, the plain milling cutter can be nomenclature as follows. The main frame of the cutter on which the teeth rest to form an integral part is called as body of cutter. It is the diameter of the circle passing through the peripheral cutting edges. It is the surface of cutting tool against which the chip is forced in the metal cutting operation. It is the back part of the tool adjacent to the cutting edge. The flute is the chip space between the back of the tool and the face of the following tool. The cutting edge is the intersection of the face of the tool with the leading edge of the land.
So it was the last video. And we continue the calculation using this sketch of our path. Dear students, our time is finished. Please finish your calculation and load your conspects, your notes, and with these laboratory works to our Telegram group and to the course in the Moodle. So for now, we finish our lesson. Goodbye. See you next week. Goodbye.